In 2028, Los Angeles will host the Olympic Games, creating one of the most complex logistical hurdles any modern city has ever faced. Organizers have to manage a staggering volume of variables simultaneously. They are tracking millions of attendees, sprawling temporary infrastructure, and nearly unlimited security threats. Yet, despite having access to high-end monitoring technology, cities managing these mega events operate at a severe disadvantage. They are essentially flying blind. The core issue is that legacy security infrastructure is purely reactive. Relying on human eyes to spot a threat in a dense crowd means that by the time an anomaly is noticed, the critical minutes needed for an emergency response have already evaporated. Current urban monitoring relies on disconnected silos. Cameras, ground patrols, and legacy radios operate independently, unable to communicate in real time. Attempting to close these gaps by hiring more guards creates a severe economic bottleneck.
Costs scale linearly, but blind spots remain wide open. Because human-centric models cannot scale geometrically to match the size of a mega event, securing modern cities requires a completely different mathematical approach. Aerial robotics was formed specifically to solve this scaling problem. Founded by spatial computing and aerospace veterans Dan Mapes and Wilhelm Cashin, they are building a new AI operating system designed for autonomous aviation. At the center of this platform is a software concept called Active Inference AI. Instead of passively recording, this system continuously learns its environment, rendering a living, three-dimensional model of the city block. This active mapping allows multiple autonomous agents to coordinate in real time. The system stops reacting to past events and starts predicting anomalies before they develop. To execute this software in the physical world, the platform deploys a fleet of FAA-compliant autonomous drones, operating continuously from surface level to 400 feet. On the ground, these aerial units sync with mobile patrol vehicles, like the AR-1, and an IoT sensor mesh. These units process data at the edge of the network for an immediate localized response. Fusing predictive software with air and ground robotics creates a true digital twin. It provides event organizers with a permanent, integrated view that effectively eliminates urban blind spots. Before this technology ever reaches the Olympics, it faces a critical proving ground in the 2026 Las Vegas pilot program. Here, the system will patrol high-density hospitality corridors. Operations maintain a strict human-in-the-loop command center, ensuring operators can override autonomous actions and escalate responses when necessary. Securing FAA regulatory approval and proving the technology in Vegas establishes the operational precedent required for the 2028 Olympic deployment. Vegas provides the exact controlled environment needed to take this active inference model from a theoretical concept to a battle-tested public safety tool. Looking past the 2028 Games, the question becomes how this technology scales across global infrastructure once the Olympic spotlight fades. The exact same autonomous architecture that secures a stadium easily pivots to disaster response. These fleets execute real-time search and rescue mapping during wildfires or large-scale floods. It also creates permanent smart city utilities capable of continuously monitoring critical power grids and executing autonomous last-mile deliveries for urgent medical supplies. This chart outlines the timeline, starting with a $3.5 million round for the Vegas pilot. Post-Olympics, projections show steep growth. Driven by scalable SaaS and municipal contracts, revenue targets $115 million, with a $500 million valuation by 2030. This projection relies on aerial robotics successfully capturing a slice of a much larger $820 billion global smart city market. The objective is to replace static surveillance with a permanent, predictive digital nervous system that monitors the city in real time.